Hi, it's Kate, and this is the first video for week 12 of Math 23. We're going to begin with implicit functions, and for a moment before we dive right into the material, take a moment and remember the last time you heard about implicit functions. You may be thinking to yourself that you've never heard about them. That would probably be incorrect. You've heard about them when you did implicit differentiation, when you were trying to find the derivative of a function that involved x's and y's, but that couldn't be written as simply as y equals something entirely in terms of x. The x's and y's may have been multiplied together. They may have been sort of sprinkled throughout the equation, but you still knew that if you selected a value for x, there wasn't a ton of choice that you had as far as selecting a value for y. And so in the lens of univariate calculus, a lot of the time when we talk about implicit functions, the only time we run into them in sort of the calculus curriculum is when we do implicit differentiation, where we take this function that is x's and y's all mixed together, and we still figure out how y is changing with respect to x. Those are the same types of functions that we'll be talking about here, where if you choose the value of some of the other variables, you're not really left with much of a choice for the ones you haven't decided on yet. And it's true whenever you have some statement of equality, there are a certain number of choices you can make. Oh, maybe x is this and y is this, but then you can't just choose anything for z in order for equality to hold. And so those are the types of functions we'll be talking about, where implicitly one of the variables is a function of the others, even if you cannot write it as x equals blah, 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 or y equals blah, 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 or z equals, what have you. And so that's what we'll be talking about in this case. Let's start with something simple, where we absolutely could isolate that variable all by itself. That's the linear case. So we have n unknowns, we have n minus k equations. In our particular example, we'll have n equals 3. We have 3 unknowns in here, and k equals 1. So we have 2 equations, right? We have 2x plus 3y minus z equals 0. We have 4x minus 2y plus 3 equals 0. How can we figure out some information about these implicit functions? Well, first, let's create an n minus k, right? Here's the n minus k side, by n matrix T. All we've done is strip the coefficients off of the x's here, the y's here, the z's here. And if the matrix T is not onto, its rows or the equations are linearly dependent. They're basically saying the same thing, only the whole thing is just multiplied by a scalar in one of the other rows. If we don't have that, when we row reduce, we'll find that we'll have n minus k, in this case 2 pivotal columns, because we can't have 3 pivotal columns here. We don't have enough rows for there to be 3 pivotal columns. So we find that we have 2 pivotal columns and 1 non-pivotal column. We assign values arbitrarily to the active variables. They correspond to the non-pivotal columns, and the pivotal columns are the passive variables. So suppose that we now reordered everything. We reordered the unknowns so that the active variables come last and the passive variables come first. And so now, if we did that and instead we had passive, passive, active, we would have up here these n minus k columns, because they row reduce into pivotal ones. There would be like this little submatrix here, this square guy right here, that forms an invertible square matrix. And so now the matrix is broken down into a form where we have a square matrix A right here. Not only that, but it's all of the passive variable information, so it's all the pivotal ones there. A is invertible, B is not. So now what's interesting is that the solution vector for this is of the form v equals xy, and we put arrows here because they are multiple components. They're not just one particular value. All the passive variables are x, all the active variables are the y's, so there could be more than one of the x's and more than one of the y's. And so what ends up happening is that a solution to t acting on v equaling the 0 vector, because that's what we wanted, when t acts on v, we always have 0 on the right-hand side. That's obtained by choosing y arbitrarily and setting x equal to negative a inverse b times y. And so what we've been able to do is we've actually, without going through all the really difficult algebra of figuring out, okay, well, if I choose this value for this variable and this value for this variable, then this is what should come out for the last variable. No, what we've done here is we found an algorithm that's pretty straightforward and gives us a straightaway look at how I can take the passives and write each of the passives as a function of the active variables. And that's why they're passive. They get decided on by whatever the values of the active variables happen to be. And so here our system of equations here determines x implicitly in terms of y. So this up here, x being the passive variables and y being the active variables. This up here, you already suspected, if I chose a value for x and I chose a value for y, then, there may not be much of a choice when it comes to z. Or if I choose a value for x, depending on what's left over for y and z, maybe there's no choice for y and z either. Because if you choose a value for x, you're left with two unknowns in two equations with two unknown system, which does have a unique solution. So in this particular case, it depends on what the actual two functions you're looking at are, two equations that you're looking at are, but in this particular case, you know that if you choose a value for x, you're going to have already decided what the possible values for y and z may be. So this is a very interesting result. Instead of having to go through all that algebra, this is a very straightforward, automated way of determining exactly how to write out these passive variables in terms of the active ones. Now let's make it a little bit more complicated. Let's talk about the linear case. The nonlinear case. We just did the linear case where it's very easy to see, if I selected a value for x, then there's only one possible outcome for y and z. Well, what happens if it's not quite so straightforward? Now, things get a little bit more complicated, but not quite so much. Say we have a point C in Rn, a neighborhood W of C, which is basically an open ball around C, the points very nearby to C, and a function f, which maps from this neighborhood to Rn minus k. So f is a function for which f of c equals 0 and df evaluated at c is on 2. F is basically imposing constraints. F is saying, I only care about points that obey a particular relationship in this neighborhood. What do we do? Well, the variables are ordered so that the n minus k pivotal columns in the Jacobian matrix, which correspond to the passive variables, come first, same as before. Let A be this sort of multi-component point that is the passive variables, and C at C, and then B is the multiple component active variables at C. So A and B can each have more than just one value. They could have an x1, x2, x3, something like however many we're dealing with, because we haven't really specified here. So the implicit function g is going to express the passive variables in terms of the active variables, which means that g acting on b is going to give us a, because b are the active variables, a are the passive variables. And for y, these are just points, right? These are the active variables near b. So the values of the active variables near the point c. This function g is going to do the same thing. G is going to be able to take those active variables and return the passive ones. It determines the passive variables such that if you plugged in the active and the passive variables into the function big F, we would get 0, because that was one of the constraints here. So all this is saying is that there's this implicit function that describes the passive variables in terms of the active variables, and it describes them so precisely that it still satisfies this initial condition that we were given, that when you plug in these points into F, we should be getting 0. So what is happening? If we adjust slightly these active variables, G tells us exactly how to adjust the passive variables so that the constraints are still satisfied. By sort of explicitly telling us how each of the passive variables is described in terms of the active variables. So if we change the active variables, we know exactly how to adjust the passive variables so that this overarching relationship, which involves the actives and the passives, is still intact. Usually, whereas it's much easier in the linear case to write down this implicit function, it's much easier to solve for it. That is definitely not the case in the nonlinear situation. So normally we can't find a formula for the implicit function that says this is how each of these passive variables is described in terms of the active variables. But what we can find is its derivative at the particular point that we care about by using the same recipe that worked in the simple case. So what do? We evaluate the Jacobian of df at C. We extract the first n minus k columns to get an invertible square matrix. We let the inverse of this matrix act on the remaining k columns. So we use negative A inverse B. And so we find that that is going to lead us to the derivative of the implicit function, which is a function of B, the actives, is equal to negative A inverse B. And we're going to talk about how to prove this and how to reason about it in class. It's a little difficult to think about because all of a sudden, you can't even, just as in univariate calculus, you couldn't write down this implicit function that said y equals blah, blah, blah in terms of x. You just have to trust that this, once you've actually been proven this in class, you will trust it more wholeheartedly. But you have to trust that this will give you the correct derivative of that function. It's going to tell you exactly how you need to change y if x is adjusted slightly.